what will be the natural frequency if the spring is up in length? Okay, so later I'm going to do this experiment slightly more, but with a bigger sample. It's probably you wait me a second. Okay, go out and get the spring in. Okay, here we have a spring, okay? So this is the swing key as you can see here. So the itself is this is unloaded when it is under its own weight. Okay, it was being pulled. Okay, by its weight, let's say to have this length. Okay, so you can do experiment to measure it. We can do it. Can I have two volunteers? 你们两位同学，拿一个计时，然后你拿一个10秒钟 OK。面对同学 ，OK， 稍微延长一点。平衡位置在哪里？平衡位置在哪里？要弹簧平衡位置在哪里？平衡位置在哪里？来，同学指教一下，平衡位置在哪里？上面就这样看。你手要动啊，不能伸下来啊。再不够再拉，那平衡位置在哪里？平衡位置大概就等它停 ，OK， 然后我再去拉它，大概是平衡位置 ，OK， 然后拉它，拉你的手这个平衡位置啊，以你的手做参考，OK， 平衡位置在这里，来拉，来同学开始算频率哦。来，你计时喊3、2、1，10秒钟来，来再来，3、2、开始。4、5、10秒，多少？7、8、10秒。不要喊停啊！不要。OK， 来，什么时候喊开始？什么时候喊停啊？3、2。10秒 ，OK， 7、8，再来一次，做实验做3次。One more time， 3、2、1，开始。1、2、3、4、5、6、7、8、9、10、11、12、13、14、15、16、17、18、19、20、21、22、23、24、25、26、27、28、29、30、31、32、33、34、35、36、37、38、39、40、41、42、43、44、45、46、47、48、49、50、51、52、53、54、55、56、57、58、59、60、61、62、63、64、65、66、67、68、69、70、71、72、73、74、75、76、77、78、79、80、81、82、83、84、85、86、87、88、89、90、91、92、93、94、95、96、97、98、99、100、101、102、103、104、105、106、107、108、109、110、111、112、113、114、115、116、117、118、119、120、121、122、123、124、125、126、127、128、129、130、131、132、133、134、135、136、137、138、139、140、141、142、143、144、145、146、147、148、149、150、151、152、153、154、155、156、157、158、159 大概10秒里面有7到8次，对不对？
嗯。
0.7到0.8。然后说半长呢？这半，就现在 ，OK， 差不多这里。所以实验之前，你们先说看，到底是比较快还是比较慢？
比较快。
嗯。来，
快。
频率更高的请举手。So is the frequency going to be higher or lower? Okay, all agree higher. Then let's do the experiment.
1、2、3、4、5、6、7、8、9、10、11、12、13。
10秒。OK， 12次。来，我们再来一次。对，好。3、2、
1、2、3、4、5、6、7、8、9、11、12、13、14。
OK， 12、13好。OK， 好，我们就时间就到这里。好，谢谢两位同学。OK， so next, yeah, the experiment is done. Then let's talk about what happened here. Why the frequency is not derived from the equation of motion? Okay, according to the equation of motion, for a mass spring system, okay, my natural frequency is square root of the stiffness, that is the 0th term of the second ordinary differential equation divided by the coefficient of the second order term. Okay, 0th term coefficient divided by the second order term. Okay, and then the frequency you measure is 1 over 2 pi omega, that is 1 over 2 pi k over n. 来，同学说说看。这个弹簧全长还是系数是 k， so the spring constant of this is k. The mass of that is n in total. Okay. So what happens if you half the spring? If you half the spring, is the mass half?
Yeah.
Okay. Is the stiffness half? So what should be the stiffness? Spring constant. 来，一半的举手，给2倍的举手。来，你们没有答案，不举手来，再大声得到一点。So what is the stiffness? What do you think? If my length is half. This is the full length. This is half the length. So I wait for you until you give me an answer. The starting stiffness of the full length. I'm asking for stiffness. Okay. So what is the stiffness? If the full length is k, what is the stiffness when it's half the length? Okay. 好，还是记住，好，等于是这样，全场是可以。你要多来一点点，我看你发在这里。
没有，我没听懂为什么。
还是记住，全长是 k，
哦，
半长的。
二分之 k 啊。
来，他说是1/2 k。然后我们问下面的，What's the stiffness?
OK。
Right. What's the answer? What's the stiffness? Okay. 这个蓝色。OK。OK。哇。对，几个。这来，后面。这个后面。2K。2个 K。来。2K。2K。来，这个女生。K。好。来。K。OK，来这边，还没讲答案，来 ，OK，来，OK，讲过了，在后面，讲过了，来在后面，或者answer或者 statement，可以，来，OK。OK，是外层。OK，来，OK，来，你好像
不知。
Ideally is 2K. Okay. But I don't know how to measure. So how to measure the stiffness? Hey, can I have a spring fan? 就这个女生，我们让你做实验。你站着，然后再找一个助手。要怎么做这个 K 跟这个几个 K 的实验？我们就用这个场景 ，K 是多少？是或者 stiffness of this。所以这个实验要怎么进行？要找这个 K 值。要找 K 值要怎么找？我们就用这个实验这个背景，来看，who want to assist？ 来，或者是另外一个老师。好，来，这样肯定会问 L 跟 K 有没有表情？2跟 K。没有，我不知道我们做实验，那怎么做？怎么做？不知道，不行啊。来，旁边在这里。你做助理还是他做助理？他说，我做助理，我做助理。先把它吊起来，吊起来，吊在上面。你可以把那个拉下来，不用把它。然后下一步要怎么？赶紧吊好来，想办法吊。抬上来。再高一点。天空位置在哪里？这样我嫌不够高，再高一点。OK， 天空位置在哪里？OK， 来，我们女同学标一下平衡位置，用那个白板。OK， 所以我们以一根粉笔做重量单位。OK， 那怎么办？
重量单位。
那怎么做？K 值怎么找？ How do you find the K in this simple experiment? 你有没有其他道具？你要想办法，我只给你一支粉笔。来，同学有没有双面胶的？啊，你看。
类似的东西。
啊，可以，你看，好帮手。
走向。
啊。
走向。
掉在最下面，你就掉这样，好 ，OK， 可以，啊，可以，差不多，来，OK， 好，开始了，跟这里，来，另类同学投影一下。实验可以用一个点吗？
差不多吧。
不可以吧？Okay, what's the kernel that you're going to do? We are doing the Hooke's law. So you're going to measure the expansion versus the cos. Okay? So, okay. So, we can first do the free vibration test. 来，刚才的同学在计时，然后你就给我算自然频率。来，怎么做 free vibration？我忘记了。来，有什么给他有自由诊断？来做什么？How to do free vibration? How to excite the free vibration? 啊？来，第三场。哎，你要等一下，先用例子，还没例子。六啊，大概，一共是再往下。3、2、1，开始。到，OK， 6次啊。OK， 看，再来一遍。OK， 标一下平衡位置。平衡位置在哪里？OK， 好，我们现在已经有一个这个应该怎么说呢？这个是如果它是弹性系数是 K 延长 ，OK。延长，这个是delta，然后这个是 k delta 1，k delta 2 ，OK， 就是这样的一个趋势。OK， 就是频率的话，我们再做一个实验，其实 往外，
重来。
3、2、1，开始。
六六。
OK，再来一次。3、2、1，开始。
六。
OK，这个是很奇怪哦。前面我们先回到静态。长度减半，请问，这个要谁讲？
那个谁讲啊？
长度减半，请问你的 K 值是增加还是减少？So now we go back to static. Since the dynamic is a little bit complicated, now we going to half the length of the spring. 来，要怎么把弹簧变半长？
弹簧变半长，
啊，
把它剪一半。
好惩罚。
你看弹簧半长，手烫的工具，用你的
把它粘起来。
来，弹簧半长，我们把它。
不手感。请你这。
非常感谢这位同学提供材料。半长，全长是多少？你要自己抓一个。直接平到要平的。
好，这样。
那你去森林，这个一定可以活命，我们节省。现在我们拉到刚才的这个位置，这个平衡位置在哪里？现在我们调一下，平衡位置调到刚才。So now we do the test。这个弹性系数到底是一半，一样，还是2倍？
哦，2倍。
Okay, we're going to do the test to prove the spring constant. Okay. Yes, please mark the first loading. Okay. And then next, second loading. What is the equilibrium position? Okay, please mark it. OK， 好，把数据画在图上面。你还有一把尺吗？来，再去找红笔。来，红笔有尺吗？Anybody have a ruler? 好，这个。来，量一下，然后这个是 you have two weights, right? This is one drop weight. Okay, this 好，喂。了解这个长度。点要不要在哪里？好，好，好的，直接。啊，第二个半长的，
半场的，
你这是全长还是半长？
是全场，是全场。
对，半长。
该不会是半场？全场，全场。
对，这可以了。你这，还是给到没有啊？哎，来同学，他对还是错？你要给他几分？来，我们有验证指证，来，
好，
对还是错？他这个标单，他这个是对号入座，已经有答案。
我用量的。
你量的，那个刻度一样吗？确定？
确定。
同学的指正看。来，比较硬还是比较软？Is it harder to have half the length of string? harder， harder 啊？所以答案是什么？一定是大于 BK。OK。刚才另外一个是已经到底，刚才是底，对吧？第一次重量跟第二次重量，那这个是到底，第二次是到底，
第二次到底，
哎，第一次
学到底
学到底啊，学到底。
那这是加2加11。
你确定吗？水量问题同学，你觉得最终刻度两倍重量的时候，一样还是不一样？就是加两个那个粉笔的时候，啊，不一样，差多少？量一下，差多少？6公分，来画一下。来画一下，差多少？是变多了还变少？所以你画的这个是全长还是半长？
一个是全场，一个是半场。
因为我问你这条线一开始是
哦，一开始是半场，我下面这个数据是全场。
那全长怎么画？ 半长还是全长
对，是全长。
？OK
这是
OK，这线是重还是不重
哦不重，
？OK，来换一个颜色。所以全长是哪一个？来，画一下名字。OK， 好，好，OK， 好，谢谢两位。所以看到没有？这个 K 值 for full length, the stiffness for full length is this green gradient, and then the stiffness for half the length, okay, is this white line. So based on the gradient, you can see that the full length one is lower than half the length one. So your answer of K and 2K, okay? K is not right. 2K is not right, so it's in between. So you can see that our ideal stiffness calculations, okay, is not quite right, okay? Because previously our spring is based on stretchable line, which is perfect elastic. But your actual spring here is helical. The helical spring has a feature that the stiffness don't change with the length. Okay? Okay, but by right, if you go for a Z, ideal spring, okay, this is K, this must be 2K. Okay? Because given the same force, okay, your extension is N over K. But here, okay, the extension under the same force, this must be K over 2, K over 2. Then they add up to be K, okay? But in this case, what is the sum? The sum is then the same force divided by 2K plus force divided by 2K. Okay? If you half the length, ideally the stiffness is double. Okay? So that's why we do it, even though this is by feel. Okay? You got your answer right. This is by formula. Okay? That's why in exam, yeah, those by feel cannot be considered completely answer. But by experiment, those say double the K cannot be right because the physical spring is different from your simple formula. Okay? 这告诉你什么？读书不要只看公式，然后还做实验。做完实验的不要只看实验，你要看一下公式，看一下你实际弹簧的形状。Okay? So that's why here also will show you, oh, how come the frequency remain the same? 来，我们来解释这现象。质量1是6赫兹，质量2也是6赫兹，那什么？这出现什么问题啊？When you pull the spring with one shot weight, the natural frequency is 6 Hz. When you pull it with 2 shot weight, natural frequency is still the same. So, 什么东西变化了？
因为这个，我照理来说是要往这个弹簧的中间，可是那个弹簧的重量跟那个比可能差不多。
然后重量有变吗？
哎，那一点，因为它执行位置有关。
执行位置有换。所以你觉得是分母出了问题？OK。来，我们再问看其他同学。来，后面的，你觉得这个都是6赫兹？哎，2倍重量哦，为什么频率还是一样？ 位同学讲的是，哎，弹簧直径下降了，所以这个双倍重量。那简单公式，来同一的同学，这个实验你做过很久了，跟我们公式不符啊。对，质量增加，哎，这我频率没掉。So what's the reason why when I double the mass of this mass spring system, why the natural frequency remain the same? 只有两个哦，公式只有两个，一个 K 一个 N。然后我们举个手，跟 K 有关的举手，跟 N 有关的举手。OK， 2倍的质量，频率一样。2倍质量的时候，频率应该变高的，举手。So when you double the mass, the frequencies go higher or lower? Lower. Okay. So this formula is underestimating the measure frequency. So when you double the mass, if the frequency remains the same, then what happens to the student? 质量倍增的，跟频率一样，所以套公式的话 ，K 应该怎么样 ？K 应该2倍。So you say, so the change of stiffness with the stretching has to do with the inclination of the spring. Why is that the case? When you are doing the small extension, the spring is having a bending. But when you are doing a long stretch, the spring is subjected to torsion. Okay, helical spring has this nature. Itself is deformed with a combination of bending and torsion. At low angle, it is bending, so not so stiff. But at this large inclination, then you have more torsion, and you then also have axial forces. OK， 好，所以这简单的实验告诉你，你实际的实测结果跟我们简单理论有距离，但是我们还是需要这个简单理论，起码它告诉你趋势，大小。OK， 所以一个很好的指标到底弹簧是变硬的还是变软的，就是看频率。So a very good measure of stiffening of the structure is based on the natural frequency because this is going to have a ratio, stiffness and the mass. Mass cannot change much. Okay, even if you increase the mass, equivalent mass, okay. It won't increase double. Okay? So how does the equivalent mass increase with the long stretching? I will come back to that. Okay? But yeah, indeed, equivalent mass will tell you it's going to be lesser if you have a long stretch. Okay? We'll take this. We are quite familiar with vibration now. Now we can proceed with more theory. Okay, so it's a revision. When the spring being stretched and then let go, then you're going to start the oscillation. This overstretch will then have more spring force than the weight. Okay? 所以下次老师要出问答题哦，要叙述这个弹簧为什么弹回去 ，OK， 然后弹完回去过后，过了平衡点，为什么提高，然后速度下降，然后又返回？So what's the reason why you have oscillation? when you release the overstretched spring and mass. Okay, that of course, when you have the spring overstretched, the spring force is greater than the weight. Then the spring force will pull the spring up to the equilibrium position. Then the spring, okay, have the spring force balance with the weight. But at that moment, the velocity is non-zero. So the mass will then keep going up with a given kinetic energy until they go higher up. At the higher point, the spring force is lesser than the weight. Then the weight will start pulling it down. So in that way, you go on. Okay? So we have previously written this force balance at the equilibrium position. Spring force is equal to the weight. Okay, but next, you're going to excite them by extra extension. This is what we call dynamic extension. And this will give you extra spring force, more than the equilibrium spring force. So as a result, then your equation of motion cannot be written based on Newton's second law, not Newton's first law, because there is acceleration once you release it. And the full equation is mass times the dynamic acceleration is equal to the weight minus the spring force. Because the spring is overstretched, then you have x plus delta. And also because the weight is balanced with the equilibrium spring force, then mg and minus k delta is cancelled out. In the end, then you have the equation of motion mx lambda dot plus kx. Okay, and then upon substituting the harmonic motions into the equation, then eventually you can find that there is a frequency equation. This is what we call frequency equations as a pre-multiplier to the assumed solution on the left hand side. And right hand side is zero applied force, zero applied dynamic force. Then as a result, then you're going to have this from multiplier to zero. And from that equation, then you find out the natural frequency. Angular natural frequency is the square root of k over n. And if you convert them into the frequency in terms of 1 over second or hertz, then it's going to be angular natural frequency divided by 2 pi. 所以你们的角频率跟频率的关系，频率是1秒钟几线，角频率是1秒钟多少度，360度是一个周期。OK， 所以这个时候你的这个要转换成1秒钟几下 ，OK， 就要把角频率除以2个派。OK， 所以这可以see the example of the hammer. Okay. So now, other than spring, what else you have? You now have the torsional spring. A torsional spring is the one that will create the recoiling portions. So one of the example is the swing door. In the case of the entrance of the bar, you might have a swing door blocking the view, but still admitting the people. So let's see how the spring door look like. Okay, the reason of it, you can see it. Let's see. Okay, let me see here. The spring door. Let's see the spring door. On this video. spring door is to remain at the closed position once you release it. Okay, this is a double hinge door hinge. One fixed to the door frame, one fixed to the door. So you can adjust the tightness of the spring. And you add lubricant. So when open by force, then it will spring back. Okay. Okay, this is a spring door. Okay, so how do you write the equation for the spring door? Okay, let's see. Okay, to write the equation for the spring door, okay, you can easily calculate. If I model the spring as the one with the torsional spring constant, how do you do measurement of the torsional spring constant? I need to add the weight at 1. Then I'm going to have one angle. I add the second weight, then I'm going to have a second angle. So this one times the moment arm, okay, will give you the torque versus angle. This torque has the torsional spring constant K theta. Okay? So with this, now we can write the frequency Newton's second law to find out the natural frequency of a spring door. Okay? So this is the mass M. Okay? So if you now swing it, okay, by an angle theta. So if you go and calculate the moment inertia, I think we did that before, but I wouldn't repeat it. So this is J naught is equal to Jg plus Md squared. When the center of gravity is half the length, okay? So your Jg is ml squared over 12. And what is your d? D is the distance away of the center of gravity from the axis of rotation. So in this case, this is half L squared. So altogether, you can find mL squared over 3. This is the J naught. And then your equation of motion is moment inertia about the pivot point times the angular acceleration is then equal to force. Because I'm talking about a spring door, the gravity direction, okay, if there is a spring here, the door direction is in the plane perpendicular to the gravity. So there won't be any gravity acting on this door, but you are going to have this torsional spring constant. So together, then you're going to have these equations, which is moment inertia and angular acceleration times the spring constant times the angle. So now what is the natural frequency? By looking at the coefficients, this is the term, the coefficient for the zero order term. So that's P theta. And this is the term for the second order term. So then you're going to have J of the denominator. In this way, you can find out. Okay? So the natural frequency is 1 over 2 pi times the square root of torsional spring constant divided by moment of inertia. Okay? So this is another resonance. Where do you find a good use of this torsional spring? You can find them in your mechanical talk or mechanical walk. 所以你如果有一个机械表，什么牌子的机械表很出名？啊，来，大声一点。劳力士，对，不是电子表，这是机械表，OK，劳力士，OK。So here you can see these spiral spring, okay. So where's the mask? Where's the mask for this Rolex pendulum? Where's the mask?
Golden one,
This is the one, the bottom one.
the middle.
Okay, 这像轮子一样的。Okay, so in this case, you have a torsional spring together with this wheel. Okay, this wheel carrying the mass along the ring. Okay. So what is the quick calculation of the moment inertia for this? Look to the moment inertia. The ring has a radius r and the total mass m. What is the moment inertia for this? Okay, if you go in quick check, then you can use the kinetic energy to calculate half mv squared sum. And then is equal to j naught half angular into c sum. So from this relationship, you can find your j naught is equal to the total mass and the radius. Because most of the velocity is along the radius, not at the middle. So in that way, you can also find how mechanical clock works. 好，我们看一下。
只有这颗无籽葡萄，没有种子。Uber Eats 吃了用的就降低。
I'm Jake O'Neill, creator of Amgrass, and this is how a mechanical watch works. Watches have no battery, microchip, or circuitry. Watch parts are machined to near perfection at microscopic sizes and tolerances, and can produce accuracy within 2 to 3 seconds per day. Let's take a high-level view before diving into specific parts. Power is stored in the mainspring and released in reliable increments by the escapement assembly. The gears that connect the mainspring and escapement turn at various speeds, allowing the watch to tell
So this is
time.
a torsional
Now let's
pendulum.
look at each section.
So it's turning to and fro, and this is the escapement.
The crown is pulled out to set the time and pushed in to wind the watch. The setting jumper has indents to keep the crown mechanism locked in place. Each mode engages different gear sets. When the crown is pushed in for winding, the sliding pinion meshes with the set of gears connected to the mainspring. The crown is pulled out to set the time. When the crown is pulled outwards, the setting lever clicks into the second indent in the rigid setting jumper. At the same time, this setting lever presses against the spring-loaded yoke. The yoke moves the sliding pinion into connection with time-setting gears. Let's see that transition a few more times.
Yeah, main idea is just to watch the mainspring. Okay.
The mainspring is a thin, nearly foot-long strip of hardened metal coiled into a spring and contained by the mainspring
So
barrel.
it must be perfect elastic so that
It's
it won't
connected
stick.
to the winding pinion at one end and the mainspring
You can
barrel at
wind
the other.
to store the elastic energy.
The winding pinion moves independently of the barrel. A connected ratchet wheel and click assembly allows the pinion to rotate in only one direction, keeping the spring from unwinding and ensuring that spring power can only exit through the barrel.
So when the spring going to and fro, clockwise and counterclockwise,
The wheel train.
the ratchet is only rotating in one
The
direction.
wheel train drives time-keeping hands and associated wheels. The center center wheel is driven by the mainspring barrel and rotates once per hour. It holds the minute hand, and its 60-minute journey is often divided up into minute marks on the watch face. The third wheel flows power through to the fourth wheel. The fourth wheel rotates once per minute in incremental ticks and holds the seconds hand.
So you don't know the gear ratio
Watch
between
makes
the
it easier to see how many
this
seconds have passed with
leading
one
down and the second down.
revolution. The axle of each wheel rests in a synthetic jewel bearing. The near frictionless jewels can keep internal watch mechanics running smoothly for decades. The Motion Works. The Motion Works allows watch hands to be freely rotated for time setting and also performs a 12-to-1 speed reduction for the hour hand. Since the center wheel and minute hand rotates once per hour, the hour hand needs to make a much slower journey, completing a full rotation once every 12 hours as it passes by hour marks on the watch face. This speed reduction is achieved as power flows from the cannon pinion through the minute wheel to the hour wheel. The cannon pinion and hour wheel are press fit to the pinions that support them. This means that with enough force, they can be moved for time setting without disturbing the rigid underlying wheel train that otherwise drives them.
Okay, so with this, then we are done for the video. Okay, let's come back to the. Okay, next, we're concerned about the distributed mass. As you can see, when you do the experiment already, the actual spring is non-ideal. Okay, you can see the spring here. Even when I remove the shock at the bottom, okay, so the spring itself can still vibrate by itself. Okay. You can see this. Okay. So you can see this. The spring has the mass distributed along the length. So in this case, how can we model the spring using a simple mass spring model? In the case of simple mass spring model, the spring carry no mass. Okay? The mass is all located at the tip. So in this case, how do you find out this mass? Okay, is it going to be the full mass, or is it going to be half mass? Okay. 来，同学，我们来看一下这个弹簧。弹簧我们已经刚才告诉大家怎么分析弹簧，我们回顾一下。What's the formula for the spring? So if this is 1K, what is the total spring constant for this? Okay, so the extensions for this one spring is delta. The total extension of this spring in series is 2 delta. So what is your effective spring constant? It's going to be F divided by K. Is there going to be 1 delta and 2 delta? This is then going to be the same force divided by K plus the same force divided by K. Okay? So what you can see here, if you have the spring in series, then you have 2F over K. So effectively, you can define the spring constant to be the inverse of that. Once you do the inverse, okay, then you're going to have half the effective spring constant. Okay. 所以你是如果是串联 是你如果是并联的 ，but if you're going to make them in series, okay, given the same extension, the first is going to give you the F1 is equal to K delta. The second one is going to give you F2 is equal to K delta. If you now sum up the force, okay, you're going to have 2K delta. So you now have F divided by delta. Then you have the stiffness double. Okay? So that's the formula. So this is what you learn in your statics. Now we're talking about the dynamic inertia effect. Is the inertia or the mass is distributed along the length. Okay? To find out the equivalent okay, if you now have one mass moved by displacement x, then its velocity is x dot at the tip of the spring, and then x double dot being the acceleration. The kinetic energy of this system is then going to be half mx double dot, half mx dot square. 所以这个动能呢就是末端的位移，得到的末端速度，然后末端的速度比方成这个质量 ，OK？ 但是你如果是单拿弹簧 ，OK， 不是末端质量。But if you now consider the spring with the self weight, the total weight of the spring is Fx. If assuming they are equally distributed, at the position R, with a small length dr, okay, then it must corresponding to one small mass. This small mass must be equal to the total mass divided by the full length, okay, times the small length, okay. So in that way, what is the kinetic energy? Your kinetic energy in this case is going to be, a small kinetic energy is going to be half small mass and the velocity, okay? If you are assuming the velocity is linearly changing, so in this point R, okay, has a velocity y, okay, and y is equal to the r over the full length times the t displacement, okay. Then by y dot square can now be written as the position over the full length square and the t speed square. Okay, so in that way, the only variable is r. Okay, and this one also is going to be written as full mass divided by full length and partial of the length, and then times the length square divided by t speed square divided by l square. Then you're going to have half m over l cube t speed square and then r square dr. If you now do the integration from x equal to 0 to x equal to l, this integral is now going to be l cube divided by 3. So upon substitution, L cubed divided by 3 into this expression, then you're going to have the kinetic energy can be expressed as half 1/3 the spring mass times the t speed square. So in this case, you now have the effective mass. Okay? 是看到没有？所以你的弹簧是分布质量的话，你的等效质量 ，OK， 要小于 你的总质量，你的等效质量只有你总质量的1/3。OK， 所以同学看到吗？ So in this way you can find out what is the equivalent mass for the spring cell. Okay. 来，我们再谈谈看。So just now we talk about the wind spring. Okay. So if you do the calculation, if half the mass, because the supporting point has 0 velocity, the tips have the maximum velocity. So the kinetic energy stored by this mass spring system is going to be 1/3 of the current calculated from the tip spring. Okay, so then you're really going to consider how the equivalent mass is. Okay, 我们再看一下那个影片。So where do you have the equivalent mass other than this simple helical spring? Okay, so in this case, tuning fork, a springboard are all going to have the distributed mass. Let's see. So that's the video. So that's the sensor key. Okay, and then this is the tuning fork.
This is a standard tuning fork used to the piano. The particular pitch or note of this fork is a C, a middle C on a piano. This note here. That corresponds to a frequency of 523.3 hertz. So if you get a tuning fork pitch for a muffin, this block of red, and place it up against a wood surface, the vibrations resonate, and we can hear the tone clearly. For fun, we decided to plunge the tuning fork into a bowl of milk and film it with a high-speed camera so we can look at the result in super slow motion. Here you can see the ripples forming on the milk surface. If you look at the vibration of the tines, it appears to be fluctuating.
Okay. Yep. So now let's count the C. So in this case, how do you calculate the natural frequency of the spring that have distributed mass? Okay, we can still apply the mass spring model, but now you got to have the spring constant being the equivalent spring that's supporting the mass. And second, the spring and the mass must be taken to be the equivalent mass. Okay? So spring supporting a big mass. Spring itself has a small mass. So as a result of the equivalent mass, so what is the idea about equivalent mass? We're lumping all the kinetic energy of the whole spring to the tips of the spring. Why we are saying lumping? Because for the spring, as you can see here, the spring, at the supporting point, there are no displacement. But at the tips, the displacement is the largest. So what about the kinetic energy in the middle? You can say half the speed. If half the speed, then it's going to be, if you square it, then it's quarter to the kinetic energy at the tips. So what you do is, rather than taking care of velocity which is changing from the root to the tips, now you are lumping all the kinetic energy at the tips, and then say, oh, my mass is getting smaller in terms of the amount of kinetic energy stored. Okay? 好，这个弹簧本身，这个是如果一端固定，一端移动，所以它的末端的这个动态速度，是最大的，顶端是零速度，所以这个时候它所储存的这个动能，它的等效质量就只有原质量的1/3。OK，在这样的情况底下，这个弹簧储存的动能 全部的质量。OK，来，同学做做看，这个弹簧只有它1/3的质量，来主动的。那我们问一下其他同学，这个后面这个左边的同学，弹簧在怎样的情况底下，它的动能是用总质量来算的？啊？这个时候动能是1/3质量，储存在1/3，就是它储存的动能只有1/3的质量。但是弹簧什么时候才储存的动能是它整个质量？So how much? Just now in the case of the vibrating spring, so only the stored energy, okay, in terms of the tip velocity, carry only kinetic energy amounted to 1/3 the full mass. Okay, in what situation you have the spring stored in the whole spring? Okay, in what kind of motion? 就在什么情况底下，它的动能呢是储存在整个弹簧上面。OK， 这样的运动呢？这样的运动呢？那请问这个等效质量多少？ So the spring is vibrating this way. How much the equivalent spring constant? How much the equivalent mass? Is it going to be more or less?
Less.
Less, yeah. If you're going to have the full storage in the full mass, there is only one case. That is when you move in the projectile motion as a whole. Okay, something like this. Okay. So in this case, the spring energy stored is stored in the complete body rather than partial of the body. Okay, so that's the whole idea. Okay. So you can see here what we did just now. So here you can see this is the full length. And if velocity is assumed to be linear, velocity and the location can be written in this way. That is the position divided by the full length times the tip speed. That will then be your velocity at a particular point. Okay? And when you now apply this formula, the kinetic energy is equivalent mass times the tip speed equal to the total kinetic energy. That total kinetic energy is contributed by small mass along the length of the spring times the velocity squared, and if you sum it up, okay, that small mass is the total mass divided by full length times the small length. That small kinetic energy will then be the small mass times half times the velocity squared, and substituting the velocity information, assuming the linear distribution of the velocity along the length, then you're going to have this expression eventually coming to have equivalent mass equal to 1/3 the total spring mass. Okay? So with this, then we have done the spring part, okay? And the distributed mass. 好，这里顺便回顾一下你们的这个弹簧公式。这弹簧公式有这个2个弹簧。这个并联，然后那个等效弹簧系数是2倍，也有这个2个弹簧串联，等效弹簧系数是它的这个小于1。This is formula that you must be familiar with. And of course, there are many types of the spring. You have the torsional spring, even though all written in K, but they have different units. In this case, for torsional spring, the unit is Newton meter over angle. In the case of axial spring, the linear stiffness is Newton over meter. In the case of torsional spring, the stiffness is Newton meter over angle. In the case of helical spring, you can see that helical spring is more complex. But surprisingly, you see that helical spring is length independent. 所以看到没有？我们刚才做实验啊，这弹簧减半，哎，半在哪里 ？OK，G is the shear modulus, D is the wire diameter, a bigger R is your helical coil radius. So this spring is independent of your length, spring constant. 哎，为什么这个很重要 ？Why is it important to have a spring independent of the length？ 我们来问一下，哪位同学没有回答到？来，我们来问一下。Okay, why is this important? You got the situation. Length independence is important for the spring. Why helical spring have spring constant? Okay, helical spring and the spring constant being independent of the length. In one application, this is important. Okay, many ways do you apply this helical spring in real life? And you want the spring constant independent of the length. Okay. Yeah, so if you go to market, you know helical spring is important. If you go to buy a fish, 5 kg, and you go to buy a fish, 1 kg. Okay, if the spring constant change with the length, okay, then the 5 kg fish and 1 kg fish, okay, will be scaled differently. Okay, you cannot read the reading of the weighing scale if the spring constant change with the length. 所以这样的一个螺旋弹簧很重要的用途呢是拿去做吊秤，比如说你钓完鱼，一个5公斤的鱼，一个20公斤的鱼 ，OK， 就用一个弹簧跟钩子勾上 ，OK， 如果弹性系数因为它伸长而改变，所以这个时候，哎，你的这个就不能依据长度来直接跟重量成一个等比关系。So the important thing of this helical spring is this spring constant is independent of the length. Okay, of course, you have other spring based on the bending. This is a cantilever bending. This is a double clamp bridge line bending. This one also. They are all length dependent and also displacement dependent. So you cannot use it that simply. Oh. And that's it for the first part. Then we now move on to the second part of free vibration. Okay, the second part of the free vibration is about the what we call the how do you calculate the natural frequency from the energy. Okay, we have learned a little bit about how to use the energy method to calculate the equivalent mass. Okay, but can you use the energy method directly to calculate the natural frequency? Okay. To define a mechanical system, we basically have two kinds of energy: potential energy and kinetic energy. And among the potential energy, we divide them into gravitational potential energy and elastic energy. In the case of bungee jump, if you jump from a height, you have the potential energy decreasing as you lower down. As you are stretched to an elastic cord, and when the elastic cord is being stretched, then there will be a gain in the elastic potential energy. Okay? And during the free fall, you're going to have the velocity increasing so that your kinetic are going to increase up to the point when the spring is stretched. Then you start having the spring force overcoming your weight. Okay, and then in that case, then you will have velocity decreasing. Then you're going to have kinetic energy decreasing down to the valley where your velocity becomes zero and where your kinetic energy becomes zero. Okay, so in this case, okay, so force acting on this mass is minus mg. Okay, if your reference of the height is upward, force is now negative. Okay, so these denotations or convention of the sign is all based on your coordinate. If your coordinate is upward, gravity is negative. Okay, so the force required to overcome the gravity is minus this gravity. So minus become positive. So, and then the work done to overcome the gravity will then be a positive lifting force. Then there will be lifting up the weight. So in the end, by integral of the constant with respect to the height, then eventually you find the gravitational potential energy being the weight and the height increment. Okay. So next, okay, if you now lift it up, there will be increment of the height. Then your gravitational potential energy is a gain. But if you are letting it down, come down, then the gravitational potential energy will drop. Again, then there will be a negative. Okay. Another kind of the potential energy is stored in the spring. This is what we call elastic potential energy. Okay. The spring force is opposite to the displacement. If you stretch the spring will try to spring back. Okay, for example, if I now stretch the spring, okay, then you can see the spring force direction is opposite to the extension. Okay, so and then the work done to do the stretching is now going to be in the same direction as the displacement. So the force will be kx. So when I'm applying the force to stretch the spring, this positive force is now in the direction of your spring extensions, and then the work done after integration of the spring equivalent force to overcome the spring force will then be equal to half the k the spring extension squared. Okay? So by drawing, you can see the force applied to do the stretching of the spring. Then there's increasing. And then the work done of the applied force will then be the area under this force extension curve. Okay? So in that way, so you can see the spring force and the spring elastic potential energy is equal to half the k times the total extension. So this includes what is called the static extension and dynamic extension. Okay? So next, then you have definition of kinetic energy. So this is obtained by the what we call the integral of the work. Okay? 这里的这个，我们这个是复习一下你们之前的动力。So how to obtain the kinetic energy? So if you are now multiplying A times displacement, the right hand side is your work done. And then your left hand side, what is it? What is your A? Your A is dV dt. Can be written as dV dx and then ds dt. So this expression can now be written as if now both side is multiplied with ds, then you're going to have a ds. So a ds is now going to be b dv. Then it's going to be b squared minus b naught squared divided by half. So if you multiply this here, then you have the work done is equal to half mv squared minus b naught squared. So in that way, we obtain the definition of kinetic energy. So it's going to be equal to the work done. Okay? So this is going to get kinetic energy. So the starting formula is Newton's law in the linear direction. If you are going to Newton's law in the angular direction, okay, then you're going to have the kinetic energy expressed in terms of half the moment inertia times angular velocity squared. Okay, so this is the and then what are the moment inertia? You can obtain that from the basic formula. You have the rod rotating. So the moment inertia about the center of gravity is 1/12 times the total mass times the full length of the rod. And then how about the disc rotating? In this case, the moment inertia is half the total mass of the disc and the radius squared. And if you now have the rod rotating not about the center of gravity, but rotating about at the distance away from the center of gravity, then you're going to apply the parallel axis theorem. So your moment inertia about the center of rotation is equal to moment inertia about the gravity plus md squared. D is then the distance between the gravity center to the axis of rotation. 所以你要算这个转动惯量的时候 ，OK， 如果它不是照着自心在转动，而轴心在自心以外，那你就要加上额外一个转动惯量值。这转动惯量值基本上就是你的这个总质量乘上这个转动中心跟自心的距离平方。Okay, so that's the moment inertia. So after this introduction and revision, now we come to apply the energy method to the free vibration. So you can apply to two cases. One is the pendulum case, the other is the mass spring system. So let's see. One of the very important understanding is, in the case where you have no external work done, okay, if the total mechanical energy only come in two forms. That is the kinetic energy and the potential energy. So they remain constant over the time. Yeah? So it means that the springs are subjected to no external work. The pendulum is subjected to no external work. 我们看一下。Okay, let's draw the spring. Mass and spring. So when it's vibrating, why we can say the kinetic energy plus potential energy is constant? And therefore external work done. Okay, let's ask the question. Are they work done by the reaction force in the mass spring system? 来问一下这个支撑这个弹簧的作用力，支撑点的作用力有做过吗？为什么？没有位。对，就是没有位。So in this case, so the system is conservative. You have spring, you have the mass. Okay. However, if you not consider opposite case, okay. Okay, let's consider another case. So in this case, you have a spring attached to the wall, and then the mass sliding on the ground. If if the oscillation is going this way, does the energy conserve? 来，我们问一下那个同学，这个情况底下，能量守恒吗？
对，
为什么？
如果没有摩擦力跟消耗，
OK，因为呢，可能在表面上摩擦，所以就有摩擦力，所以让表面不熟。Okay, so these are the two cases. Okay, so let's see the video. Okay, so in this case, you will see that you're not going to have a virtual motion when the mass is sliding along the floor, unless the ground is frictionless. Okay, yeah. So you have to add some lubricant. Okay. In most cases, the oscillation is going to be short line because of the friction is going to take out whatever energy you have. So in these two cases, you cannot apply the energy conservation. Okay. So pendulum is a case that where you for sure have energy conservation. So that's because the supporting point has no motion. So if you now have a pendulum, okay, supporting a weight. Okay. Even though you have a swing, okay, but the air friction is minimal. Okay, so in this case, then you are not going to have okay. Let's watch the video. Okay. So in this case, you are making pendulum out of the durian. Okay, are you afraid of durian? 'So this is a pendulum swing experiment. If you now have a pendulum made out of durian as a string, and you release it from the height, will the durian hit you? Okay? Okay. Okay. So in the case of potential constant conservation of potential energy, the durian will not hit back when you release it still.
如果就是把榴莲推出去，说榴莲会不会打到我的脸呢？
If you push the durian away upon the release, then it will bang onto the wall. Okay. Okay, based on this, now we're going to analyze the conservation of the durian pendulum. Well, the position when you release, okay, it has the highest potential energy. And once it's released, they are lowering in height, and then they will convert the potential energy into kinetic energy. They'll gain it the speed, and the speed till it overshoot until the opposite position. And then in the opposite position, the kinetic energy will all be converted into the height. 所以你在释放榴莲过后，这榴莲的力呢会转换成动能，然后这个它就有了速度，有了速度它就会让榴莲跑到对面去，然后超过了对面这个速度，这个动能呢又逐步转为位能，所以到最高的位置它就停了下来，然后就开始转向。So in this case, we know that the motion of the durian pendulum, so it is a swing between position 1, 3, 1, 3. So if you now doing the plot of the swing angle, so that position, okay, if you now draw the pendulum made of durian. You made the durian pendulum. And monitor the angle. going to have this oscillation. So from the oscillation period, then you can find out the frequency. Okay? So this is what we call the angular position. If you do a time differentiation of the angle, okay, then you're going to start with the velocity. Okay? Okay. So a sine curve after you do the time differentiation will become cosine function. And because your variable is pre-multiplied by omega, so your derivative is going to pre-multiply by omega as well. So your angular velocity is now going to be omega times the amplitude of the angle. So if this is the angle, this is the maximum angle, what we call here is the amplitude. Okay, this is your time varying angle. If you now differentiate it, then you're going to have the angular velocity is now natural frequency times the amplitude of the angle times cosine omega n t. Okay? And now this is what you call the amplitude of the velocity. It's natural frequency times the displacement amplitude. Okay? So you can see that we turn a sine function to be a cosine function. Okay? But of course there is a phase. The starting phase in this case is 90 degrees. Okay? So here, let's analyzing what is the potential energy when the durian was lifted. Okay. So in this case, when durian was lifted, okay, so let's find out the datum. The datum is the lowest position where durian is. If the pendulum length is L, okay, this is your datum of